Hi guys, I will explain tire brush model on combined slip from assumptions to combined force and moment. Here I have a quiz for you. In the following equation representing the bristle force of the sticking region due to combined slip, which one is the right expression for kappa Tx or kappa Ty? Number 1, kappa Tx equals kappa Px. Number 2, kappa Ty equals alpha. Number 3, kappa Ty equals tangent alpha. Number 4, kappa Ty equals tangent alpha over 1 plus kappa Px. Let's look at what is combined slip and what types there are. In the last video, E53, we looked at the brush model related to side slip. And in the last video number, E54, we looked at the brush model related to longitudinal slip. At this time, let's look at the combined slip, in which both side slip and the longitudinal slip occur at the same time. Combined slip occurs when braking in a turn or traction in a turn. We need two assumptions to make a brush model for combined slip. The first one is for bristle stiffness. Both lateral and longitudinal bristle stiffness are assumed to be equal to each other, as shown in the equation 1. The second one is for normal force distribution. Tire normal bristle force is assumed to be distributed in the parabolic shape with the maximum bristle force 3Fz over 4A as the same assumption made earlier in the brush model for side slip and longitudinal slip. The roadmap to establish the brush model for combined slip analysis is all the same as those of side slip and longitudinal slip, except for additional steps to define the combined slip and to calculate the pneumatic trail for self-aligning moment calculation using the concept of equivalent side slip angle. Therefore, I will not repeat the same explanation here, since the combined slip of the brush model can be used for both of braking and acceleration from now on. For the convenience of explanation, the combined slip of braking in a turn will be mainly explained. Let's go through step by step. Let's start with the sticking region. In the sticking region, the tire contact patch changes in a straight line according to the combined slip without the sliding. Bristle bases attached to the tire don't show any deformation, but the bristle heads attached to the road surface are deformed into the shape of a green straight line. At this time, the displacement of each bristle head is produced the complete opposite to the direction of slip velocity. Combined slip is neither parallel to x-axis nor to y-axis. Therefore, we should newly define the combined slip and formulate the equation for that. If the stiffness of each bristle is defined as Cp, the bristle's combined force and moment equations can be established based upon bristle displacement and bristle stiffness. The order of analysis for sticking region is define the bristle stiffness per unit length and find deformation of a bristle, define the combined slip, and finally formulate the combined force equation. For the calculation in the sliding region, we can assume that bristle normal force Qz is distributed parabolically along the longitudinal axis as described in the blue parabola. When it comes to braking in a turn, the bristle bases don't show any deformation, but the bristle heads are deformed into a red parabolic curve. Since the horizontal force applied to each bristle is the quantity obtained by multiplying the normal bristle force by the tire friction coefficient mu, the red parabola represents the maximum horizontal force distribution. Therefore, the horizontal force equation of the bristle in the sliding region can be established by integrating the equation for parabolic curve of red region. Therefore, the order of analysis for sliding region is assume parabolic normal pressure distribution and calculate the maximum combined force. Finally, formulate the combined force equation. In the next step, we have to calculate the sliding start point at which the sticking region and the sliding region are separated. At the sliding start point, the combined force in the sticking region and the combined force in the sliding region coincide with each other. Using this, the x-coordinate of the sliding start point can be calculated. Once the x-coordinate of the sliding start point is determined, the combined force in the sticking region and the combined force in the sliding region can be calculated by integrating the deformation equations separately. And the resultant combined force and moment for entire tire contact patch can be obtained by adding these results together. The second new procedure in combined slip analysis is to calculate the pneumatic trail TC. Pneumatic trail TC can be calculated using the principle that the pneumatic trail due to yellow combined bristle forces equals that due to red pure side slip bristle forces. Consequently, we can calculate the self-aligning moment as a result of multiplying the previously obtained lateral force by the pneumatic trail Tc. Therefore, the final step can be summarized as calculate the point at which the sliding start, integrate the equations separately, calculate the resultant force for sticking and sliding region, finally calculate the pneumatic trail and moment. When braking in a turn, maximum horizontal force distribution of tire contact patch gets reduced in the beginning region and gets expanded in the following region. Therefore, parabolic shape of maximum horizontal force distribution inclines rearward. This curve inclines frontward for the traction in a turn. Let's think about the combined slip by braking in a turn. This figure shows the force and the slip speed in the tire contact patch when braking in a turn. Deflections are produced in the direction completely opposite to the slip speed vector Vs, because the bristle stiffness of any direction is the same on the entire horizontal plane, and the friction property is the same at every point on the entire tire contact patch, including both the sticking and the sliding region, because material property of bristle is isotropic. Let's look at the displacement of braking in a turn. In the brush model, the displacement of a bristle in the tire contact patch is produced along the only one straight direction, completely opposite to the slip speed Vs, even though we have two kinds of slips in both lateral and longitudinal axis. Consequently, combined slip is also produced along the only one straight direction, completely opposite to the slip speed Vs, and the displacement due to the combined slip can be expressed by the x component ux and the y component uy. Now let's formulate the displacement in the sticking region. When braking in a turn, a bristle displacement in the tire contact patch can be described as two components, one in the x-axis, named ux, and the other in y-axis, named uy. In the similar way to the longitudinal slip brush model we learned in the video number E54, the absolute value u can be expressed as the equation 2. Furthermore, ux and uy can be expressed as shown in the equation 3 and 4. In the vector and matrix form, u can be expressed as shown in the equation 5. Let's define the slip speed for combined slip. As in the displacement, slip speed Vs of a bristle in tire contact patch can be described as two components, one in the x-axis named Vsx and the other one in y-axis named Bsy. It can be expressed in the vector equation 6. The equation 7 shows the absolute value of slip speed Vs, and the equation 8 shows the matrix form of slip speed Vs. At this time, we have to introduce new theoretical slip, kappa Tc, for combined slip brush model. Since it has 2 degrees of freedom, it can be expressed in terms of x component, kappa Tx, and the y component, kappa Ty. They are defined as the equation 9 and 10 respectively, using the definition of theoretical slip, which is the minus ratio of slip velocity to the linear speed of rolling, Vr. Absolute value of kappa Tc can be expressed as the equation 11. Equation 12 shows the vector and the matrix expression of kappa Tc. Let's formulate the displacement equation in terms of theoretical combined slip for sticking reason. Rearranging the equation 5, we can get the equation 13. As shown in the equation 13, it can be seen that the displacement vector u can be expressed in terms of theoretical combined slip defined earlier. Therefore, we can get the equation 14 using the combined slip component kappa Tx and kappa Ty. This expression is kappa Tx and this expression is kappa Ty. Combined slip component kappa Tx can be expressed in terms of a practical longitudinal slip kappa Px. Let's prove it. Directly from the figure, we can get the equation 15 as an equation of linear speed of rolling, Vr. Substituting Vr of equation 15 into the equation 9, which is the definition of kappa Tx we obtained earlier, we can get the equation 16. Dividing numerator and denominator of the equation 16 by Vx, we can get the equation 17. This expression is none other than kappa Px. Therefore, we can get the equation 18 for the theoretical combined slip component in x-axis in terms of practical longitudinal slip kappa Px. Combined side slip component in y-axis kappa Ty can be expressed in terms of practical side slip tangent alpha and the practical longitudinal slip kappa Px. Let's prove it. A practical lateral slip is defined as the equation 19. On the other hand, theoretical combined slip in y-axis is defined as the equation 10. and which linear wheel speed Vr can be expressed in the equation 15. Substituting minus Vxy over equation 19 and Vr over equation 15 into the equation 10 and dividing numerator and the denominator by Vx respectively, then we can get the equation 20 in terms of practical longitudinal slip, kappa px, and the practical side slip, tangent alpha. Now, the equation for the Bristle displacement in the tire contact patch can be independently established along the x-axis and y-axis. For the x-axis displacement, equation 22 can be obtained by substituting equation 18 of the combined slip kappa tx into the equation 21. For the y-axis displacement, equation 24 can be obtained by substituting equation 20 of the combined slip kappa ty into the equation 23. Therefore, the displacement of Bristle can be expressed in the matrix form as shown in the equation 25, and in the vector form as shown in the equation 26. Consequently, Bristle force vector Q in the sticking region can be expressed with the Bristle stiffness Cp and the combined slip kappa Tc as shown in the equation 27. Let's look at the Bristle force depending on the region. This figure shows the Bristle forces in the sticking region marked in blue and the sliding region marked in red for braking in a turn. In the beginning blue region of tire contact patch, displacement linearly increases depending on the straight green line because Bristle force is less than maximum friction force distribution mu qz, as in the equation 28. In the following red region of tire contact patch, decreasing normal Bristle force qz is not enough to keep up the increasing linear displacement, as in the equation 30. Therefore, Bristle force is restricted by the maximum friction force distribution mu qz. In other words, horizontal Bristle force cannot exceed maximum friction force distribution mu qz. There is a tire bristle on the borderline between sticking and sliding region, at which the force of sticking region becomes equal to that of sliding region, as in the equation 29. Abscissa of that bristle is called xp. Now let's move to the Bristle force in the sliding region. Referring to the figure, it is clear that a Bristle force vector can be expressed as the equation 31. Using the relationship between kappa Tc and Vsc as shown in the equation 32, and the previously obtained definition of Vs of equation 7 and kappa Tc of equation 11, we can formulate the equation of a Bristle force vector Q as shown in the equation 33. Let's get the Bristle force expression in both the sticking and the sliding region to calculate the Abscissa xp required to solve the integral equation of force. Bristle forces of sticking and sliding regions should be the same at which sliding starts. Therefore, having the earlier obtained equations of Q sticking of the equation 34 and the Q sliding of equation 35 equal each other, we can obtain the equation 36 which can be expressed as shown in the equation 37 using the explicit form of QZ. Now let's calculate the abscissa at the sliding start point. From the previously obtained equation 37, we can calculate the abscissa xp, at which the forces of sticking and the sliding regions are the same. Arranging the equation with respect to xp and using the definition of theta, we can get the equation 38. For the isotropic material, theta equals theta x and theta y, as in the equation 39. Now we can calculate the force in both sticking and sliding region using abscissa xp. From now on, developing equations is very easy job because all the equations have the same forms as those developed in both side slip and the longitudinal slip. Let's go on sticking region first. In the same way as before, we can get the integral equation 40 for sticking region. Then we can get the equation 41 after integration. Substituting the early obtained xp into the equation 41, we can get the equation 42 for sticking region. Next, let's move to the sliding region. In the same way as before, we can get the integral equation 43 for sliding region. Using the early obtained xp of equation 38, we can calculate the equation 44 to get the force in the sliding region as the equation 45. Using the previously obtained equation 38, force equation can be made in simple form. To simplify the breaking force equation, it is necessary to introduce a factor lambda and the parameter theta. The factor lambda is the ratio of distance from the beginning of tire contact patch A to the sliding start point xp to the entire longitudinal length 2A of tire contact patch as shown in the equation 47. Please remember that A is always positive and xp is a coordinate value, so xp can be positive or negative. When lambda is 0, sliding occurs on the entire tire contact patch, and when lambda is 1, sliding does not occur on the tire contact patch. Using lambda, the coordinate xp of sliding start point can be expressed as in the equation 48. Parameter theta is defined as the equation 39 to simplify the expressions. Since the equation 38 and the equation 48 are the same sliding start point xp, lambda can be expressed as shown in the equation 49 by substituting 0 for lambda into the equation 49. The longitudinal slip kappa t sliding, at which sliding occurs over the entire tire contact patch, can be obtained as shown in the equation 50. And the theta at this time represents a reciprocal of the longitudinal slip kappa t sliding. Previously obtained equation 50 makes us get the combined slip kappa tc sliding when the sliding starts all over the entire tire contact patch. Now, let's move to the calculation of the resultant combined force. The resultant combined force is sum of forces in the sticking region and the sliding region, as shown in the equation 51. The first one is a linear region, and the second one is a nonlinear region. Therefore, resultant combined force can be explicitly resulted in the equation 52. Using the earlier obtained equation 49, we can simplify the resultant force expression as the equation 53 and 54. Let's calculate the lateral force and the braking force. Equation 54, derived above, can be expressed as the equation 55 using the relationship of equation 49. Since the force acts in the completely opposite direction to the slip speed, the force component Fx and Fy can be obtained as in the equation 56 using the combined slip, which is the function of speed. Further on, the braking force can be expressed as in the equation 58, and the lateral force can be expressed as in the equation 59. The self-aligning moment can be obtained by multiplying the lateral force Fy of equation 59 obtained here by the pneumatic trail. In the case of combined slip, since the direction of force is not perpendicular to the x-axis, the self-aligning moment cannot be obtained by direct calculation, as in the case of side slip. Therefore, we have to calculate the pneumatic trail Tc first. Then, the lateral force obtained by the equation 59 must be multiplied by the pneumatic trail Tc to get the self-aligning moment. To get the idea for calculating pneumatic trail, let's first look at how to find the moment arm length for the multiple forces tilted by the same arbitrary angle theta with respect to the y-axis. How can we calculate the moment arm of inclined force? As shown in this figure, let's assume that three forces with arbitrary magnitudes from F1, F2, F3 act with respect to the x-axis with the same inclination angle, theta. Since the component force on the x-axis does not generate a moment about the z-axis, an equation for a moment mz with respect to z-axis can be established with the component force in the y-axis only, as shown in the equation 660. The resultant moment mz can be calculated as shown in the equation 60, in which right side equals the sum of moments produced by y components of all the forces with respect to the z-axis at the origin C. The resultant lateral force in y direction can be obtained by summing all the y components of each force as shown in the equation 61. So, the moment with respect to z-axis at the origin can be obtained by multiplying the resultant lateral force Fy in the y direction by the moment arm length, which is the pneumatic trail Tc, as shown in the equation 62. The equations for mz and Fy obtained above can be expressed using F1, F2, F3, and the inclination angle theta as shown in the equation 63 and 64, respectively. The pneumatic trail Tc can be obtained by dividing the moment mz by the lateral force Fy. And since the trigonometric function cosine theta is present in both the denominator and the numerator, it can be eliminated. Therefore, it can be seen that the moment arm length, which is a pneumatic trail Tc, can be obtained using the forces F1, F2, F3, and the x-axis coordinates x1, x2, x3 regardless of the inclination angle of the forces as shown in the equation 65. Let's look at the equivalent side slip angle alpha equivalent required to obtain the pneumatic trail TC. Referring to the pneumatic trail, in the case of tilted force, we have learned the pneumatic trail TC produced by the sum of bristle forces of the combined slip in yellow equals that produced by the sum of bristle forces of pure side slip in red with the same magnitude as that of combined slip. This can be explained with one bristle. The pneumatic trail produced by combined slip force in the thick yellow has the same pneumatic trail as that by the same size pure side slip force in thick red. Let's find out equivalent side slip angle alpha equivalent using this figure. If the yellow combined bristle force at the Abscissa XP, where the sliding starts, is rotated vertically like this, it becomes a red arrow. And the red arrow represents the bristle force due to pure side slip. When the end point of red arrow and the start point of tire contact patch are connected in the black straight line, the angle formed with the x-axis is the equivalent side slip angle alpha equivalent. We can find the equivalent side slip angle alpha equivalent in the other way around. Let's take a unit length 1 backward from the beginning point of tire contact patch. The theoretical combined slip of the bristle at that point is kappa Tc. If the kappa Tc is rotated vertically like this, it becomes tangent alpha equivalent of red arrow. When the end point of this red arrow and the start point of tire contact patch are connected in the black straight line, the angle formed with the x-axis is the equivalent side slip angle alpha equivalent. Of course, tangent alpha equivalent has the same magnitude as the combined slip kappa Tc. Therefore, it can be seen that pneumatic trail Tc produced by the pure side slip has the same magnitude as that produced by combined slip. Therefore, by substituting theta kappa Tc in place of theta y tangent alpha equivalent in the equation 67 and the equation 68 obtained from the previous video number E53 related to the side slip brush model, we can get the equation 55 and 69 in terms of theta kappa Tc. Then, the pneumatic trail Tc produced in the case of combined slip can be obtained using the equation 66. Therefore, by substituting the equation 55 and 69, the pneumatic trail Tc can be obtained as in the equation 70. And by multiplying this pneumatic trail by the lateral force of the combined side slip obtained previously in the equation 59, the self-aligning moment mz for the combined slip can finally be obtained as in the equation 71. Let's think about the Bristle force by traction in a turn. This is the mixed view. upper axis perpendicular to x-axis represents the vertical z-axis, and the lower axis perpendicular to x-axis represents the lateral y-axis. A maximum horizontal force distribution goes inclined to the front because of traction force. If there are neither traction nor braking force, its shape will be parabolic symmetric with respect to the lateral axis passing through the center of tire contact patch. This figure shows the displacement and slip speed in the tire contact patch. Displacement are produced in the direction completely opposite to slip speed vector Vs because the bristle stiffness of any direction is the same on the entire horizontal plane, and the friction property is the same at every point on the entire tire contact patch, including both the sticking and the sliding region, because material property of a bristle is isotropic. Therefore, each bristle in the tire contact patch experiences along the only one direction completely opposite to its corresponding slip speed Vs. This figure shows the bristle force and the combined slip speed in tire contact patch. As I explained earlier, deflection of each bristle is produced in the direction completely opposite to its corresponding slip speed vector Vs. So does the combined slip kappa Tc. Consequently, a bristle force Q also is produced in the direction completely opposite to its corresponding slip speed vector Vs, because bristle force Q is proportional to the combined slip kappa Tc. Let's think about the direction of displacement. Depending on what I explained up to now, any bristle in the tire contact patch shows its displacement along the only one straight direction of slip speed Vs, even though we have two kinds of slips in both the lateral and the longitudinal axis. Consequently, combined slip is also produced along the only one direction of slip speed Vs in the brush model. Before the explanation of traction in a turn, let's formulate the equation for displacement and the sticking region for traction only. In the traction, linear speed of rolling Vr is greater than wheel center speed Vx and can be expressed as the equation 55. In the equation 72, slip speed Vsx is negative because both Vr and Vx are all positive. In the application to the traction, we can use all the equations developed in the brush model for braking as they are. When we recognize Vsx is positive in braking and negative in traction, consequently, in the equation 74, displacement Ux should be positive because Vsx is negative. Finally, substituting 72 and 73 into 74, we can express the displacement Ux as the equation 75 as the same way as in the braking. Now, let's formulate the equation for displacement in the sticking region for traction in a turn. When it comes to the combined slip due to traction in a turn, Bristle displacement in tire contact patch has two components, one in x direction named Ux, the other in y direction named Uy. In the similar thinking to the brush model for braking in a turn, the absolute value of displacement Ux can be expressed as the equation 3, and the Uy can be expressed as shown in the equation 4. or it can be expressed as in the equation 5 as the vector and the matrix form. We don't need any further explanation because from now on, all the equations are the same as those in braking in a turn. It's time to hit the answer to the quiz. In the following equation representing the Bristle force due to combined slip, which one is the right expression for kappa Tx or kappa Ty? The answer is number 4. Kappa Ty equals tangent alpha over 1 plus kappa Px. Here we have a summary. Assumptions of a brush model for combined slip are both the lateral and the longitudinal bristle stiffness are equal. Normal force is distributed in a parabolic shape. Overall order of a brush model analysis is to formulate the deformation equation, to define the combined slip and formulate the equation, to establish the Bristle force equation of the sticking region, to establish the Bristle force equation of the sliding region, calculate the point at which sliding starts, to sum up the results from individual integration for the sticking and the sliding region, to calculate the pneumatic trail, to calculate the self-aligning moment using the pneumatic trail. Considerations on braking in a turn and the traction in a turn are: displacement is defined as minus u in braking and plus u in traction. All the equations are the same. Size of slip speed depends on linear wheel speed of rolling and the speed of wheel center. If you watch the previous videos, you can easily understand the upcoming videos. In the previous video, E0055, I explained how to calculate the lateral force and the self-aligning moment caused by side slip with the tire brush model, and shows the process of deriving the related equations. Recently, in the video number H54, I explained the mechanics of a bristle based upon the bristle speed and introduced the theoretical slip, and also explained how to calculate the braking force caused by longitudinal slip with the tire brush model, and shows the process of deriving the related equations. The next video will be the tire brush model, part 4. I will explain how to make the graphs using brush model for combined slip. Please hit the thumbs up and catch the brand new videos by free subscription. So, what are you waiting for? See you on next video. Goodbye guys!